What is up, YouTube? It has been a minute since I've done an update on the Alpha project or anything in your boy's garage for that matter. So today I want to go ahead and talk about some stuff I've been working on in the background. Alpha Emulator has been steady in development. We are working on currently switching out the memory for a cheaper alternative, something that will drop the cost of the BOM. The BOM with our NVRAM is sitting somewhere around $30 or less, but I'm honestly trying to drop that to a fraction of the cost just to really help curb development costs and make sure that we have a super inexpensive emulator option on the market. With that said, the latest issue with the Alpha project, since I'm totally transparent on these things, we had some trouble with the Alpha Emulator taking updates in the ECU versus out of the ECU. So the way that we have the Alpha Emulator configured, the OE signal from the ECU is gated directly to the buffers and the latches, depending on which setup we're using. And the issue with that is when the emulator is installed in the ECU, the OE signal from the ECU is actually held low so strong that it overcomes the pull-up resistor we have on the emulator device. Meaning, if the emulator is not installed in the ECU, the OE signal is pulled high on the latches and buffers, meaning they're disabled, i.e. they're not in control, and it allows the MCU to communicate directly with the memory that we're using. So the issue is when we put the emulator inside of an ECU and the car is off, the OE signal is so low, so strong, pulled down low, open drain, that we actually are having this issue where the buffers or the latches want to be enabled, and because of that, you have two different master devices trying to talk to the memory. You have the buffers, which are trying to talk to the memory, thinking that the ECU side is actually driving it. And you also have the MCU trying to drive the memory, so you get a lot of bus contention and you get terrible writes and reads because of this. The solution has been to disconnect the OE signal from the ECU side during these updates to make sure that they work. And then when live update is enabled, we plug the OE signal back in and we go ahead and monitor that signal. So the cure for this is to actually install a gate buffer driver so that we can isolate the signals from interfering. So I have this chip here I set up. It's an isolator. I call it the OE isolator. Pretty simple. Or the OKI isolator. And basically we're using the 5-volt signal from the ECU to turn the isolator on and off so that we know when the ECU is active and when the ECU is inactive. This allows us two states for the emulator. It allows one true state where the emulator is disconnected from the ECU OKI OE signal and allows us to use a pull-up resistor, disabling the buffers and allowing the MCU as the master device. So the MCU can directly read and write to the memory. And when we go ahead and get 5 volts from the ECU, that nice little PCB enables and it allows the OKI to drive the buffers directly, letting the OKI signal take complete control. The reason that we want these separated is because when the ECU is off or offline, we're actually trying to do full bulk writes without some sort of specific sequence to it. This is just more efficient and faster. And when the OKI signal is live and pulling, we're actually using a live update sequence where we write 1 or 2 bytes within a certain time frame window based on data we're reading from the OKI signal. So we have a offline and an online update method, and by using that PCB, we are now allowed to do both of those methods. And the reason that I opted for doing a PCB like this is, as you guys have seen, I've made several revisions of the Alpha Emulator. And while I love drawing up these PCBs, making revisions and soldering these things, The reality comes down to I would have to create an entire new PCB for the emulator, put an RP2350 clock crystal on there, as well as all of the passives. I'd have to solder up another memory chip, headers, etc., etc. Versus with the Alpha Playground board that I showed you guys, the development board, I can simply interrupt the signal and use this. And this allows us to really fine tune these fine, small details of the emulator so that when everything's kind of dialed in, we'll just go ahead and respin that board, hopefully one more time, and make life a lot easier. But with that being said, I've been working on a couple of other things. Aside from working on the Alpha Emulator project, I've actually been working on some obsolete replacements for the OBD1 ECU. You guys may find online that there's a few people out there offering some replacement components for the OBD1 ECUs. The reason we have these replacement components is because the OBD1 ECUs have a few different failure points. And while we're creating these emulators, it's important to make sure that the OBD1 ECUs stay alive so that there is something for people to want to put these emulators inside of. Standalone ECUs are becoming a little bit more popular and prevalent, and the major downside to using a standalone is you're forced into something like Tuner Studio or something of that nature that is a completely different software than what we enjoy and we are familiar with. A lot of us like to use Chrome, Neptune, HTS, maybe some of us are still using BMTune. Regardless, the concept is if we're using traditional OBD1 Honda tuning software, we really want to keep you guys using that software to move forward with the tuning game. We don't want you guys rolling into Tuner Studio or something you don't have to with a standalone ECU. When these standalone ECUs kind of understand the process of the Oki processor and the way that the Honda ROM is compiled and decompiled, it might be extremely beneficial to switch over to one of these standalone ECUs when they can support the program, the algorithm, and protocol used with traditional software. Until that happens, we stress that you guys stick with the OBD1 ECUs, support the people out there repairing those ECUs, and because of that, we want to also make sure that people repairing those ECUs, maybe even yourselves, have access to the components to repair those at a fair cost. With that being said, there are a few different components and drivers inside the ECU that cause issues. I've created some alternative replacements to these obsolete components. With that being said, I have not tested these components yet. They are still in the prototyping phase. I still need to make sure that size and fit is what I want. My main priority was making sure that these components had proper cooling, tracing, and planing of the boards. I see that there's a few other guys out there who have made replacements, and while they work and I applaud their efforts, none of them are really open source with how they're doing anything. And besides that, I see such fault and issue with these layouts and designs that I figured, why not make the open source standard on these products and put them out there so that people know the correct way to go about and do these things. So without further ado, I would like to show you the Alpha line of the QM1, QM2, QM3, SK5150, IE IC14, and the HIC1 replacement modules. Check it out. So right here we can check out my 5151 SKS replacement module. This is an amazing module replacement. I kept it relatively low profile, but I can't promise the most micro size. What I can promise is amazing heat dissipation properties and proper trace circuitry throughout the project. What we have here is an IC that is a high side switch. So the 5151 that is used for switching VTEC on and off is what's known as a high side switch. And what the high side switch does is it allows us to take a positive rail, being the 12 volt rail, It allows us to take that rail and inject it from an input to an output. So when VTEC is actually commanded in the car, there's a few different things that happen. There is a 12 volt signal that sits on one side of the high side switch that we're looking at here, okay? So just picture this in your head real quick. One side of this is an input and it has 12 volts going to it all the time. The other side is an output, okay? And the output side will have 12 volts come onto it when it's commanded by the ECU. That 12 volts on the output goes to your VTEC solenoid. Now the VTEC solenoid needs a 12 volt input and it needs a 12 volt output or a ground source, a negative source. The way that the VTEC solenoid works is it gets its ground source directly from the block. We're negative, we're grounded. It's really the same signal. So when someone mentions a 12 volt negative or a ground, it's actually referring to the same network in the car. So a ground signal is the same signal as negative that is hooked up to your battery terminal. The VTEC solenoid gets negative constantly, all the time, by being grounded directly to the engine block, which is grounded to the frame of the car and back to the battery. So there is always a direct connection on that minus or ground side of the connection or solenoid. The other side of the solenoid, which is the single wire coming off of the top of it, is actually a 12 volt positive connection, and it's waiting for a positive signal from the battery to energize. The reason the ECU can't directly provide that signal is because the ECU works off of low amperage or low controlled signals, i.e. a logic level. So logic levels are something that the microchip can put out at low volts and low microamps, meaning on or off. And we need something at a true level that will work with our devices, a high logic level, such as the real 12 volt rail that's coming off the battery. Now, traditionally, what we do when an ECU doesn't have the VTEC components in it is we use an external relay. And the reason I want to touch base on this is because an external relay will kind of help you to understand what the internal components on a VTEC ECU are doing. With an external relay, you hook one pin up to your battery, you hook one pin up to your battery's ground, or the negative side. You have one pin that is hooked up directly to the VTEC solenoid, and then you have one pin that's used as a control signal. So when the ECU is going to say that VTEC turns on, it sends out a logic level. In some cases, we borrow an external output, maybe like a power steering sensor, and that sensor has a high enough logic level that it can turn a relay on. So the ECU sends out this small logic level signal that is either on or off. Let's think about a 1 or a 0 because that's how logic signals work. When it's a 0, it means off or ground. When we have a 1, it means high or on, which is a positive signal, usually set above a certain threshold. So when the ECU says VTEC should turn on, it takes one of those wires, whatever you set in your software, let's say it's the power steering wire. It takes that wire and it sends a high logic to it, meaning that it is a positive logic set to a certain threshold, and the relay will see that all of a sudden it gets a high logic on that wire, a 1. That makes the relay turn on and allow power to flow from the 12 volt side on the input to the 12 volt side on the output to your relay. It's really quite simple. Now, when we go back to the inside of the ECU, that IC14 module used for ECU VTEC conversion, when mimicking a P28 style ECU, it's the same thing. It's basically a miniature relay. And because of its micro size, what happens is there's a lot of heat generated. The original VTEC solenoid called for somewhere around 0.8 of an amp, so it was under 1 amp that it drew. But with people doing swaps, there's a lot of current or resistance that is introduced into the line from crimps and bad connections. old wiring, oil being put on the connection points, as well as the age of the components. Something that I have found personally working in an industry where we have motors that operate lifts, we find that these motors that traditionally require 10 amps to run after so many years begin to require 15 amps due to the windings wearing out and things like that. So when we look at a VTEC solenoid that was originally drawing zero point 0.8 amps potentially of current, when you factor in the age of it, the wear of it, and you factor in modified wiring or oil and things like that from the engine maybe on the wiring, you can actually experience much higher amp draw than zero point 0.8 amps. And the original SK or SI5151 used on IC14 in the ECU is actually rated for almost 2 amps. It's rated at 1.8 amps. So we want to use an IC that's rated closely to that 1.8 amp threshold. So here you're going to see in my design I have a large footprint IC. It is not a micro IC. It's actually extremely close to the original 5151 IC. And what I've done here is I've introduced a large exposed copper pore on the front and the back that is tied together with all these vias. These vias are little holes inside of the board here. And what that does is it laces the front to the back. And this gold area, this copper area, is all exposed battery voltage. This is where 12 volts comes in. And what this does is it allows this IC to remain extremely cool. If you've ever done ECU repair, you may find where people have used other ICs in place of IC14, and you can see some discoloration on the metal tabs of those ICs. And the reason for that is because of extreme heat generation that has occurred from amp draw and current resistance pulled from that device under VTEC load. So the beauty of using my replacement here is that it actually replaces the 5151 not only in relative footprint size, but in excessive cooling design. So this is designed to release tons of heat so that the IC lasts a long time. And on top of that, it is an inexpensive design. This allows you to use an IC that is approximately $2 to $3. The PCBs are pretty much cents on the dollars, especially when you panelize them. And as you can see, we're actually utilizing really large traces throughout our design. You may be questioning what these little 45-degree angles are, and this is actually a planing field that I do to prevent ground noise and things of other things coming in like EMI from affecting the board. So something you'll notice that's typical amongst alpha boards is I have this little grounding layer in here that has a pattern to it, a 45-degree crosshatch, sometimes greater, but that's kind of a trademark of something that I do, and it is in all my boards. And this IC right here uses 12 volts in. It uses 12 volts out to the VTEC solenoid. It uses a ground input as well as a control logic level from the ECU, so an on and off signal. And the one additional thing that you're going to find on these 5151 chips is there is a diagnostic pin, which is an open drain pin, meaning that it is held low or it is held at a 0 or ground reference. And when something happens on the output side, meaning there's greater draw than it expects, like a short or a bad solenoid, it will actually set that pin high or to a 1, or it will introduce voltage to that pin. So this includes that diagnostic feedback pin letting the ECU know when there is a fault with it. So this actually mimics the entire original VTEC solenoid. Pretty cool stuff, super inexpensive. I want you guys to be able to put this board in your ECU in replace of the obsolete 5151 IC, which you can still source from China, but let's be real, we're trying to be more modern and optimistic, and I have a component here that is readily available. It is super inexpensive, under $3, especially when you buy in bulk. So this device is set up for a inexpensive SKS 5151 or VTEC IC replacement on the low. Next we have the Alpha QM1 over here. This is another awesome IC that I put together and designed. It's pretty simple. It's got a couple of diodes on it. It's got a couple clamping diodes as well as a couple of switches on it. This is effectively going to be replacing a driver circuit. So QM1 as well as QM2 are your driver circuits on the ECU. QM1 handles injectors 1 and 2, while QM2 handles injectors 3 and 4. Well, they're essentially the same IC. If you actually desolder from your ECU and take a look at how it handles the traces, you'll find that it bridges a specific set of traces for QM1 and it bridges a specific set of traces for QM2. So with that being said, I've actually bridged those same traces on my QM1 IC and I bridged the separate traces on my QM2 IC. The reason for this is it offers lower impedance and direct connection to the way that the ECU is actually trying to make the hardware work instead of forcing the hardware to work. So my replacement hardware is actually more in line with what the ECU is expecting versus what it is trying to make the hardware do. As you can see, we have large copper pores. We have a nice set of switches here that have plenty of room to dissipate heat from load. These are oversized drivers for what the injector is trying to do, but let's be real. We see injector faults and injector driver issues, which causes the need to replace the QM1 IC. So why not overbuild the IC and make it tougher and more durable than it should be? This is a drop-in replacement. It will help cure issues with injectors 1 and injectors 2. Here you see QM2, which is essentially a replacement of QM1. Like I said, it just has the addition of different outputs from the ICs being bridged together to mimic what the ECU is actually expecting. Same exact setup. Beautiful copper pores, once again helping with heat dissipation, large traces to make sure that this is actually working correctly. None of that tiny baby trace bullshit that we're seeing in other designs. I love that other people are working on this type of stuff, but when it comes down to it, if you're not producing something with a set standard or something that's going to work well, we'd rather not see it in the industry. QM3 is actually slightly different than the QM1 and 2. QM3 affects a few different areas, including the O2 heater, primary cooling fan, AC fan, as well as the AC compressor. So this circuit controls 4 different outputs. And as you can see, we have 4 different drivers on the back. We can see that they share a large copper pore for heat dissipation, as well as we have several diodes to prevent backfeeding of the voltage. We also have these several diodes on here set up for TBS to prevent overvolting from the input source down to a logic level that accepts it so that it prevents burnout on the drivers, as well as we have a condition here with the resistors that is holding down a default condition, as well as a limited input current for the gate driven resistance. So there's a default hold down as well as a current limited input. It's pretty simple stuff, but some people seem to really miss out on these things and these small features, which go a long way. So this is our QM3 replacement chip. Here is our original IC for QM1 or QM2. It's this little guy right here, and that is what you've seen me replace with that beautiful copper pore setup with the exposed drivers on it. And this is QM3 that I showed you for handling the quad outputs to the AC compressor, both fans in the front, as well as the O2 sensor. And last but not least, we have the HIC1 module. So the HIC1 module is actually a comparator circuit. It is designed to take the signals from the distributor and it is designed to clean them up and turn them into a signal that the ECU understands. So the U1 and U2 ICs right here are actually the comparators on here, and the rest of this is simply a network to clean that stuff up. These small looking transistors on here are actually just diodes, and they are meant to prevent clamping. Excuse me, they are meant to clamp and prevent overvolting to the ICs, and the setup here is pretty simple. So there's just 3 inputs. They come through, it handles the crank signals, cleans it up, and sends them back to a Schmitt trigger. And Schmitt triggers are pretty cool. I use them on my Pi PLC, which is my elevator controller that I designed. And essentially, a Schmitt trigger takes a signal that goes high, low, high, low, high, low, and it kind of cleans it up to where it's either high or it's low. There's none of the oscillating that happens in between. It cleans it up. So the idea of this board right here is simply to clean up a circuit and amplify the outputs to make them work. And something I've seen with other people doing this is they're using op amplifiers in place of the original comparators, even though it's a comparator circuit. And the funny thing is when you put an op amp in place of a comparator, if the circuit is designed as a comparator, the op amp will mostly work as a comparator, but there are certain thresholds that it can't keep up with. And I've also noticed that some of these other people are using gigantic capacitors on here, which don't align with the way that the network is actually set up to clean up. So this is a complete reverse engineering of the original Honda IC for HIC1. This is not my personal layout on this chip. This is Honda's layout for the HIC1. Everything else has been my personal layout, but this is a clone, and it's just to keep parasitics and such in the circuit to help keep it working like the original board did in here. So all of the values for the capacitors and the resistors are exactly or close to what Honda called for on the HIC1. I simply repurposed the board and used smaller resistors that I like to work with. I love the 0402 package, so that is what the resistors are actually set up for, is 0402. The beauty of using this replacement here, and you can see the copper pores are damn near identical to the original Honda pores, is this IC right here can be made for well under $5, especially if you're producing it yourself, and the competition is marked up somewhere around 6 to 7, 8 times the cost of that. So this is a much more inexpensive solution. I feel like it's an even better solution, and it's more modern, using passives that are of the appropriate size. So I really look forward to seeing people using these inside of the ECU for repairs, because they're inexpensive, it's slightly modernized, and it maintains Honda's original layout. And as you can see, this is the original HIC1 board from Honda. You can see there's no components on it, because when I reverse engineered this, I didn't want to go off anyone else's work. I wanted to go off of mine. So I took every component off and measured it. I traced every IC, and I followed over the original traces to keep things OEM as possible. So I have been extremely busy. You can see I've got some ECU stuff going on there in the background. I've been 3D printing some ECU cases, as well as digging out some other ECUs with issues, and I'll be sending those off for someone else to take a look at them, who I appreciate doing the work in this industry, and I would rather support them than spend the time repairing the ECUs myself. I have other things that I would like to do. So I appreciate you guys checking in on the project. I appreciate you guys checking in on what's going on over here at Ya Boy's Garage, or in the Alpha Development Den, however you guys want to look at it. these are just the latest updates with me. I've been busy at work. I'm a production supervisor as well as an electrical engineer. So I have quite a limited amount of time to work on a lot of these things as I'm working on personal projects for the company I work for on my spare time as well as when I'm there. So that's kind of what's been going on with me and my life, and I just wanted to post an update. I know it's been a minute, and I promise to get you guys an update soon on the Alpha Emulator. It's not that it's been so far behind, it's that every time I get closer and closer and closer to finishing this project, I push something else more onto me and Dennis with making the project even better. So like I said, the goal right now with the Alpha Emulator is to reduce the cost, to make it as minimal as possible, and provide you guys with something that is functional and works correctly in one go. So we're dialing in some bugs on the software side, we're dialing in some additional features on the hardware side, and while that's happening, I'm throwing in the whole fiasco of let's change this up while we're at the near end and make it work. And it's just like taking 2 steps back before 1 step forward. So that's what's going on with the Alpha project. We haven't forgotten about it. It hasn't failed. It hasn't disappeared into existence. It's just that I have a lot of ideas going on, and while I'm working on these other things, I'm always wanting to push and pursue and make things better. So Alpha has not forgotten about the emulator. Alpha has been clearly developing other ICs for you guys to use for ECU repair. And if you're really interested, let me know. I'll drop the ICs in Gerber file with the BOMs in the comments, or maybe I'll modify the description. I'm not sure, but let's see if there's some interest. I'll drop those in and you guys can play with the prototype boards before I officially release them, and you guys can let us know how they work. I should have some prototypes and some time to do it within the next month or so, but that's 30 days out. So how serious are you guys? Do you want to play with these things and see how they work? Do you want to criticize on some of these things, give feedback? I don't know. Let me know. Give this video a like, subscribe, share it with your friends, share it with the haters. I don't care. Every publicity is all good publicity. And until next time, take it easy. That's Alpha.